Hello, everyone, and welcome again to the 7th International Electronic Conference on Sensors and Applications. Today for a session focused on students. This conference has been organized by MDPI and their journals Sensors and Chemosensors. And I would like to take this chance to thank our chairs, Dr. Stefano Mariani, Dr. Tom Messervey, Dr. Alberto Bayan, Dr. Stefan José, and Dr. Francisco Falcone. Also to all the people from the conference committee for making this conference possible, and all the participants for joining us today. During this week and until Monday 30, you will be able to assist to several live sessions with excellent speakers and have the opportunity to read and comment all the author submissions presented for the conference. Please look at our webpage during the rest of this month for more updates and register for free for the following live sessions. I would like to remind everyone that this webinar is being recorded and that we also have a YouTube live streaming. The recording will be posted on the conference webpage for everyone to watch it as soon as possible, and I will be sharing the YouTube link through the chat in a few moments. I will now present today's session chair, Stefano Mariani. Dr. Mariani is an associate professor at the Department of Civil and Environmental Engineering of the Politecnico University of Milan. His main research interests are, among others, the reliability of MEMS that are subject to shocks and drops, the structural health monitoring of composite structure through MEMS sensors, numerical simulations of ductile fracture in metals and of quasi-brittle fracture in heterogeneous and functionality graded materials, or multi-scale solution methods for dynamic delamination in layered composites. Thank you, Stefano, for accepting to participate in this session. The microphone is yours, so everyone enjoy.
Thanks, Anna, for the introduction. And welcome to our today student session. So it's a pleasure to introduce this session, which is sponsored, as Anna said, by Sensors and Chemosensors. So today we will have 9 presentations to be delivered by PhD students, and each of them will have 15 minutes for the presentation, including also some minutes for questions and answers. So I recommend everyone so since we have this quite tight schedule, to be on time with the presentation. So don't steal any further minutes, and I will say let's start immediately with the first presentation, which is going to be delivered by Marco César Prado Soares, from the University of Campinas in Brazil. So Marco, please, stage is yours.
Thank you. Hello, dear friends from the 7th International Electronic Conference on Sensors and Applications. My name is Marco from the School of Mechanical Engineering of the University of Campinas in São Paulo, Brazil. Today I'll be present to you the smartphone-based optical fiber sensors for the assessment of a fed-batch bioreactor. This presentation is a little long because we wanted to give you to those who want to check every detail. So not everything will be detailed here, but you may feel free to ask anything or send us emails or so on. Well, this work is introduced in the context of the Industry 4.0, where the application of novel mathematical and computer-based methods for the optimization and monitoring of systems presents social, economic, environmental repercussion on the activities. This new period relies on the development on new technologies. These technologies should be capable of collecting, distribution, and delivering information by themselves. So, in chemical and biochemical industry, such industries may present an increase of the data availability on the portability of the monitoring devices, and this has potential to enhance safety, productivity, energy use, environmental sustainability, and product quality. In the chemical and biochemical assessment, well, this is generally based on high performance liquid chromatographic systems, gas chromatography, as you can see here, and the GC is not here. Coupled techniques like GC, coupled to mass spectrometry, ELISA immunosorbent assay. These methods are, of course, sensitive, reliable, and very precise, but they demand expensive and book instrumentation. They demand highly trained technicians and procedures that take long, very time for the analysis. So on the other hand, the use of compact real-time sensors allows you to monitor, control, and screen the best process conditions with high facility. In this context, the optical fiber sensors presents many advantages to being applied to chemical and biochemical systems. They present reduced masses, low energy costs, resistance to electromagnetic interference. They may perform the remote sensing. They present higher environmental resistance, are inert to both chemical and biological agents. And of course, they present reduced fabrication costs, so they are suitable for the mass fabrication of devices. In this work, our approach was to develop a portable smartphone-based OFS platform that is designed for the monitoring of fed bed fermentation systems. The fed bed was chosen because it's the most way that the alcoholic fermentation industries in Brazil, that are very important industrial sector in our country, operate. And the results were validated through comparison with a handheld refractometer and with the mathematical models. So, how is the fermentation monitoring and modeling? It's usually focused on the maintenance of the adequate conditions for the microorganisms. It's based on the evaluation of the cell's concentration that is usually expressed as the X. Many of these traditional measurements are based on manual time-consuming procedures. For example, counting with Neubauer chamber, that is a technique where you remove a sample and put it in the microscope to count the cells. Dry mass evaluation, that is a technique where you take the sample, centrifuge it, and dry it to evaluate the mass. And surface plating method, that you put a fluorescent marker, a fluorescent label, and evaluate it in a specific device. So most of the practical industrial cases, in most of them, the measurements and control are actually based on the quantification of specific properties, since these other techniques are not possible. It may be either physical, example, variation of mediums, refractive index, viscosity, or electrical conductivity, or even biochemical, like monitoring the concentration of specific proteins, carbohydrates, DNA, or RNA. And the properties are posteriorly correlated to the concentration of cells by an appropriate model derived from the fermentation reaction. This is the general fermentation, where cells consume substrates, that's usually sugar, sucrose, and generates products and more cells, what constitutes an autocatalytic process. One very common way to model it is through the Monod model, that it's expressed through these two differential equations, and there are other two, the Ludeking-Perret and this one, that accounts for the product formation and for the consumption of substrates. So in the fed batch reactor, it's a mode where we start with a given volume and initial concentrations of cells, products, and substrate. Products usually 0, and an initial volume V0. So a constant feed flow F supplies it with solution containing fresh substrate and the concentration SF. So the differential equations are quite changed to take into account this variation of volume and the dilution and the accresciment, the add of substrate. So our working conditions, we use the specific lineage, the ECSA-7 of Saccharomyces cerevisiae cells cultivated in East Peptone dextrose, that is a medium already optimized in pH 6.5 to give best conditions. A feed flow containing only sucrose in water in concentration of 30 grams per liter, and the fed with a peristaltic pump. The reactor presents high surface area per liquid column, so the surface is kept exposed to the atmospheric air and the magnetic steering, guaranteeing the saturation of the liquid with air. This guarantees the aerobic conditions which are necessary for favoring the cell reproduction over the ethanol production, so the ethanol does not interferes in our measurements. These are the parameters, so everyone can perform the same simulations. And the optical fiber sensor smartphone, it's based on the modulation of the power reflectance caused by difference in the refracting index of the liquid medium. These differences are originated by the consumption of sucrose by the cells, and because the sucrose presents a very high refracting index, very higher than water. So the substrate uptake increase the medium, change the medium's refracting index, and the light transmitted is reflected back in the external medium and reflected back, and the intensity is modulated through Fresnel equation. We use a LED source, the smartphone camera LED, or an external source through a multi-mode silica optical fiber, and a coupler directs back to the camera. So when the light reaches the fiber liquid interface, part of it is transmitted and part is reflected with the intensity modulated through Fresnel law. So the reflected light is redirected to the camera, and we develop an application that processes the data. So here is the Fresnel law with a constant for correction of the power losses. And it's very important to keep all the systems, all the optical fibers in the correct position. So we develop a smartphone case for both keeping the position and to isolate from the environmental light. So this case was developed for Samsung Galaxy 9. The case contains ports for the optical fibers and for the LEDs. It was fabricated through 3D printing using PTFG filament. Here we have the full project of the case that is already supplied in the supplementary information. And here you can see the full setup where the sensor is simply applied to the liquid. The Android application was designed for processing the intensity signals in Android Studio. The operation chooses the image processing parameters, acquires the optical data by the video capture, and analyzes the optical intensity of the recorded video frames. It has three main fields to fix the duration of the measurements, the interval between measurements, and to define the resolution. It also presents other two modes, where the simple one is to perform the camera adjustments for calibration position. The second one performs the recording in a MPEG-4 extension. So after recording the video, the frames are discretized, and the application reads the camera image, collects the image, and evaluate the image average pixels luminous intention through this equation that's simply explaining how to calculate the average. And then we remove the dark regions. So we have the total number of pixels present on the region of interest. And finally, the processed light intensity data is exported to a text file where the normalized curve obtains the product concentration. So here is a simple photography. And we performed first the correlation between the refracting index and the optical intensity detected. We obtain this direct correlation for concentrations ranging from 0 to 100 grams per liter, and relatively low signal to rate that increase as the cell concentration rise due to the increase of the scattering by the cells. So we verify that it's indeed possible to evaluate the refracting index, and we perform so the fed batch fermentation. It's very important to notice that in fermentation, related high deviations from the model are usually expected because the models present lots of uncertainties, like temporal evolution of the microorganisms, adaptation to a small difference of substrate, small oscillations of temperature throughout the experiment, and difference from shear stress that stress the cells, etc. So the constant recalculation of the adjusted parameters is a procedure highly suggested. So but in our case, the mathematical predictions represented by this black line here they agree very much with the refractometer signals and also with the R sensor. So our results corroborates with the refractometer and with the theoretical model. So our refractometer presents high resolution of only 10 to -4 refractive index units, but it's also related to the high cost equipment that requires sample collection. In contrast, the smartphone-based sensor is available for online monitoring of the fermentation and predicted the concentration of ethanol of only 3.5 grams per liter, what's 5.36 times lower than the concentration of sucrose. Therefore, the ethanol effect on the refractive index can be indeed neglected. So the design of a portable and low-cost smartphone-based sensor was demonstrated with a sensitivity of 8.5 refractive index units. Due to the limited frequency of data collection, the system is not capable of performing quasi-elastic light scattering analysis like previous works that we performed, but its production are quite inferior. It can be manufactured on site by 3D printed and can be easily integrated to an industrial line. So this last characteristic is of major importance for Industry 4.0. Such integration is not possible for traditional assessment measurements like HPLC, and future works will focus on enhancing the sensitivity and to test it under higher fermentation scales for the evaluation of its performance, analyzing more complex systems. Special fibers and sensors will also be evaluated. And I'd like to thank you all of you to the opportunity to speak in here today, to São Paulo Research Foundation for 2 grants that fund this research, and for our partners, Professor Lucimara Latorre from the School of Chemical Engineering, Professor Cristiano Cordeiro from the Physics Institute of Unicamp, for helping us with the yeast strains and the handheld refractometer and 3D printed, and also to the other funding agents from Brazil. Thank you very much.
Okay, thanks. Thanks, Marco, for the nice presentation. I think we have time for 1-2 questions. So anybody in the audience? Alberto?
I have a question.
Yeah. Yes, please.
I would like to know the diameter of the fiber core, and if you have also considered plastic optical fibers instead of glass fibers. Thank you.
The fiber diameter is the standard for the silica. It's about 125 without the extra layers, no? Because we have also a layer of Kevlar and a layer of polyethylene. We are considering, yes, the plastic fibers because it allows us to perform in under more easily ways. For example, we can spin it, we can etc. But it's in the next steps of our research, of course. But by that moment, we had a little problem with the coupler. We didn't have a coupler available that worked well with the plastic fibers, but it will be used because indeed, when using it was something that we noticed that we had to increase the power of the light source because the silica power didn't transmit as well as a plastic fiber would be. So of course, if you use a plastic fiber, you will have a better intensity and so a lower SNR.
Okay, thank you.
Okay, thanks. So I think we are now at 10:20, so we have to move to the next presentation. So Marco, thanks again for the nice presentation. So next presentation will be delivered by Gerardo José Ginovart-Panisello from La Salle Universitat Ramon Llull in Spain. So Gerardo, please, floor is yours.
Thank you. I'm just sharing my screen. So, well, yes. my name is Gerardo, and I'm going to explain you my part of my project. It's a comparative analysis recording of a broiler bird intensive farm. And we are going to study the variations and the stability of the acoustic data we can get from the animals between two different campaigns, one in winter and one in summer. And why in the poultry meat? Because poultry meat is one of the most efficient biological systems that transform the cereal to high energy proteins. And also poultry meat is everyone or a lot of people eat poultry meat due to their cheap cost. So as I have said, we want to capture two entire production cycles of intensive production, broiler roast 308. 308 is the genetic of the animal of a poultry farm here in a Mediterranean farm. And we are going to study this variation of 4 metrics: the equivalent level, the peak frequency, and the variation of that 2 metrics. That is the variation of the peak frequency and also the variation of the equivalent level between these two opposite climate seasons. And the only change that we have in the farm, because we cannot control, is the animal lot. Here is we have 2 photos of the deployment of our system inside an intensive farm. We can observe that the microphone is hanged to 1 meter from the floor. The idea is to capture not just one individual broiler, it's a collective group of broilers near that microphone, and is a distance of around 1 meter from the floor, because we want to capture as much closer as we can to the animals, but also we want to avoid animals eating the microphone. And we also have on the wall the recorder of our system. Here we can see as a schematic of the farm. The farm also had different sensors, and we wanted to include the acoustical sensor at the same places or near places where we have other monitoring systems. Here we can see that we have a microphone, a dioxide carbon sensor, and also a sensor of humidity, all together in the center of the farm, and also in the outer parts of the farm we have the sensors of temperature. The idea of hanging the microphone and having this kind of microphone, this is a microphone that has a cardioid pattern. It's based on the idea of eliminating or reducing any other source of sound, because we want just to capture the sound of the animals, but we are in an indoor place, so we have reverberation of the sound, and we also get we could capture sound from other sources as fans, drinkers, eaters, something like that. So the idea or the design want to minimize the others sound sources and maximize the sound of the animals. And also we have a Zoom recorder. This recorder can record 5 days continuously, but we need a technical reset each 4 days to ensure that we can capture all the data, because here we are analyzing 44 days of life of the broiler birds. In what we are studying, we are calculating the equivalent level each 30 minutes, so we can get an idea of how loud or lower the animal is vocalizating, and also we are getting or calculating the frequency in the mean frequency value of the vocalization of the group of animals each 30 minutes. The first thing that we are doing is to having a humming window where we are getting or segmenting the audio slides with an overlap of the 40%. Then we are doing a bandpass filter. The idea is just to filter or to eliminate all the other sounds. So we are getting a bandpass filter. Then we apply an FFE algorithm, and then we are getting the max frequency of that 4 minutes. And the idea to have a more stable or value, we are calculating the mean max frequency of our system each 30 minutes. So we have the same resolution between the equivalent level and the frequency. And as I talked before, or 2 different campaigns of 44 days are going to take in two different seasons. We are using, or we are having a winter season and summer season, and the idea is to see these variations. The winter season, it's going to be the first campaign. We have from 13 to 1 grade centigrade as an external temperature and 0% of humidity, external humidity. And the second campaign, that it's being held between July and August, it gets an external temperature from 14 to 31 degrees centigrade and an external humidity from 4% to 55%. And now we are going to talk a little bit deeper with our results. We are going to analyze or compare always the same metrics between first and second campaign. The first campaign is a winter one, and the second one is the summer one. And as we can see or appreciate in this graphic, the first 2 days we are receiving the newborns of our birds to the farm, and they have a lot of stress. Why they have that stress? Because they need, or they are they don't feel comfortable and they don't know a new place. So we can appreciate that they have a higher equivalent level in the first 2 days. And also the pattern, that different pattern that we can observe from the equivalent level of the first campaign to the second one is that the first campaign, during the hours of the daylight, that it's between 4 a.m. to 18 p.m. or 6 p.m., we can observe an increase of the equivalent level compared with the summer season, where there is not this pattern. If we compare the equivalent level with the peak frequencies, we observe in the main value by days that the first 3 days have the highest frequencies vocalization, and that's due that the animal at the beginning, it has a little chest cavity, and all the vocalization are much more sharper compared with the other days. For example, we can see the decreasing of the vocalizations of the animals each days that they are growing. And also we can see that the summer campaign has more sporadical peak values compared that in the winter campaign. The different equivalent level of the first campaign shows that the first 3-4 days have a lot of more variation than the rest of the cycle. And this is the same, we have the same parameter between the first campaign to the second campaign. And also we can see some blank gaps, that is, we couldn't calculate all the values, so that's due to the computational calculation. And also the equivalent level shows during the 20th day to the 14th day that they decrease a little bit these variations. And the variation of the peak frequencies, it's completely opposite to the peak frequencies graph, because the highest variation in this case is the last days of life, when the animal has biggest chest or cavity, and then the animal creates much more variations between different vocalizations. And also we can see the tendency of this increasing of the value of these peak frequencies. At the end, going inside the discussion, we have seen that there is some invariant and variant parameters that can help us to distinguish if we are in one or another campaign. As a variant, we have seen the equivalent level captured at the arrival of the birds are the highest and long lasting. The peak frequencies captured the first 4 days is indicates high values of frequency vocalizations in newborns. The variation of peak frequencies has the major increase, and the variation of the equivalent level also has the highest and long-lasting variation during the first days of life. As a variant, we have the equivalent level in winter. There is an increase of the metrics during the daylight compared with the summer season, and the peak frequencies is in average lower during the winter campaign than in summer. And the second campaign have more sporadic peaks of this high frequency than in winter. As a future work, we have just started 2 campaigns. We want to perform much more campaigns to ensure this data stability. We want to find nonlinear dependencies using artificial intelligence algorithms. All the study is just using one sensor, so we want to start using a multi-point recording to have more spatial mapped levels inside the same farm, and also for being able to compare all these values, we want to study or to do a standard environmental noise recording, ESO, to be able to compare our values. And all this future work is going to be inside the Neurostar project from these following three years. And thank you so much. Thank you for letting me talk in these conferences, and it has been a pleasure.
Okay, thank you. Thank you, Gerardo, for the very interesting, nice presentation. We have again some minutes for a discussion. Is there anyone in the audience with a question? Well, in the meantime, I have a couple of curiosities. So the first one, if I correctly understood, so you said that basically you collect the measurements and then you do Fourier transform, and then you pick up the mean frequency, right? Yeah. Because at the beginning you mentioned the max and then the mean. And curiosity is the mean frequency enough to get information concerning, let's say, the health or so the condition for the birds?
Today, or what we have seen a lot in other publication, is that it's one of the most important indicators, because the animals, when they express stress, normally they increase their vocalization, and we can see it increasing this max value. So one of the most directly relations seen what you see with the animal, because if you go inside a farm and you start, for example, clapping, all the animals start vocalization higher. So it's at least is the first indicator to measure the stress or the healthy of the animals, but we are starting using another indicators, mostly in the future work that we want to start doing non-linear dependencies. So we are starting seeing what happens with other indicators.
Mm-hmm. And in fact, yeah, the second curiosity I had was related to the use of neural networks. So somehow you already replied to what I had in mind, because you said that you are going to do it, because so basically you provide some pictures and you can do kind of image recognition inside. And so maybe you can even increase the number of features that you may take out of these images in comparison to what you can do with the, say, naked eye.
Yeah, that's the idea, because it's very complex to understand the stress of the animals. So we want to start having a lot of more data and starting to use a neural network in the idea of trying to see, for example, comparing these acoustical indicators with the values that the farmer has. So how much they eat, how much they drink, and then trying to find some correlation related with this. Because, for example, if we found that these two indicators are related with an increase of food or an increase of thing, so then it's an indicator that the animals are in a good state of health. So that's the idea.
Well, good, very interesting. Sorry, but we have to cut now the discussion. We have to move to the next presentation. So Gerardo, thanks again for the very nice presentation. And next speaker is Novak from the Joseph Stefan Institute in Slovenia. So Rok, please, floor is yours.
Okay, thank you. Hi, my name is Rok, and in the next 12 minutes, I'll try to present you in a clear and succinct way our work regarding low-cost environmental and motion sensor data for complex activity recognition. This is a bit different title than you have in your program because I think it describes a bit better what I'll be showing you. So first of all, we can measure PM concentrations all around us. Airborne particulate matter is something that is ubiquitous in the environment. And one thing that is very important is exposure, and then in turn intake dose. So basically how much airborne particulate matter gets in your body through inhalation or deposition or other ways that can enter your body. Aggregating this kind of data, so specific activity data, what you are doing when you are exposed, for example, running or driving a car or gardening or something like that, can provide you more detailed information about what your exposure is and when is it. And this can provide you additional data. Every participant or every person who can have access to this kind of data to curtail their experience and their different activities to reduce their exposure and intake dose. But then we started to think, well, how do we obtain this data? So one way is, of course, just have a pen and paper and just write down what people are doing, or have an app maybe, which is inaccurate and time consuming. So labeling every minute what you're doing or filling in an app, that can be very time consuming and for consumers or for researchers. So we were figuring out other ways, and then we said, well, but why not try machine learning? So now we have different ways to use machine learning to actually find out some simpler activities, such as running or sleeping or certain sport activities. This is done with one of the sensors we use, like a smart activity tracker. But the thing is, we are trying to figure out if we can actually determine the specific, more complex activities that have more influence on your exposure to particulate matter, such as cooking, cleaning, or the most important, of course, smoking indoors. That is one of the main sources of elevated PM concentrations. So as I mentioned, we used a smart activity tracker, basically just a Garmin smartwatch that measured heart rate and movement. We used a particulate matter sensor, a portable one that we constructed for the purposes of the Icarus 2020 campaign, which is a Europe-wide project regarding exposure to particulate matter, to pollutants and effects of climate change. And with this device, we measured particulate matter concentrations in 3 size classes. So 1, 2.5, and 3 micrometers in diameter, and temperature, humidity, and speed. We also provided each participant the time activity diary, as I said, a simple pen and paper solution. But the thing is that we had 97 participants. We had 2 seasons of 7 days. But because we can't really tell participants to record for each minute, like so many participants that are more or less reliable or not reliable, they were just for each hour of the day. So then the next step was cleaning the data and analyzing it, and then using it in 3 classification models, as I'll explain later. So the first data analysis that we did, these are just averages for each activity. As you can see, cleaning, cooking, playing, resting, running, sleep, smoking, and sports. So we can see some very nice patterns here. Like, for example, the average temperature is lower for outdoor activities, or speed is higher for running. Heart rate is lower for sleeping. And crucially, as you can see in the second row on the right side for particulate matter concentrations, we can see that for smoking, it's much higher, and for cooking and cleaning also. So the first results were okay, let's say they were promising. We kind of expected that, of course, but these clear distinctions actually gave us some more confidence to continue with this work. So the first step was to do a PCA. which didn't really show any clear patterns. Maybe we can see in the upper right corner some basic clustering of running, but that's not really indicative. The clusters you can see on the bottom of the biplot, or on the left side, like these bigger clusters, these are basically more or less just zero values. So when there are 0 steps or 0 speed and so on. So we didn't really gather much from the PCA. That's why we took another step and tried different classification algorithms. So we used 3 algorithms. In this work, generally, we have 2 things that we're looking at. So one, can we actually predict the activity based on these parameters that we're measuring with these devices? And 2, if we can do it, which classifier shows the most correctly classified instances? So we gathered some data. We discussed with our colleagues at this institute about different approaches in classification, and we chose 3 classifiers. The first one, the IBK, is based on a k-nearest neighbor algorithm. The J48 is generally just an implementation of the C4.5 decision tree algorithm, and then random forest, one of the also the more famous ones, let's say. So these are the results. The correctly classified are all above 30. That's not the best result. This is just a proof of concept, let's say. But the random forest did actually show 43% of correctly classified instances, with also the other measures that we can see here, such as kappa and true positive and precision, were quite high. Also the ROC and the PRC area. But the thing is that, as I said before, all of the activities were per hour, and the sensors measure data by minute. So any way that you conflate these two, or taking averages, or any other way, it's not the same granularity. I can explain this, like, for example, when you go running, you basically, let's say you run for 20 minutes, you go running for 20 minutes. That's not an entire hour. Even though a participant would put in running for that specific hour, it's not the entire hour. So 40 minutes of that hour would be data that is not for running. Or even if you run for an entire hour, it's really rare that you run from like 7 to 8 p.m. So again, it's conflating between the hours. So of course, a future improvement, this is the next step we took, and I'm doing this basically just right now. I'm coming to the conclusion of the data collection, is to gather data minute by minute and see if it shows better results. So most of the, or a lot of the misclassified instances were with resting. You can see in the confusion matrices in the bottom that there were a lot of misclassified instances for resting, because it's quite a vague activity. So what is resting? Is it lying down? Is it playing a game? Is it going for a walk? So the next step in our research was to clearly define these activities and break them up in more defined ones. On the other hand, like sleeping and smoking are quite well-defined activities, but one of the most important things that I found out that again supported this this approach to actually have the data minute by minute was the sleeping. So as you can see in the sleep in part of the, I hope you can see my mouse here, the sleep in part of the confusion matrices, the sleeping actually shows most correctly classified instances. And as I gathered, this was basically the result of the fact that sleeping is usually a one block activity. So you go to sleep in the evening and you stop sleeping in the morning. So it's basically 6, 7, 8 hours of non-interrupted activities just in one piece, which means that it quite well relates to writing that down hour by hour in time activity data. the diary, and then using the sensor data to correlate it. Well, in conclusion, we can see that combining these data points with environmental stressors, that we use low-cost sensors to actually gather this data, could provide some detailed results of exposure and intake dose. And the thing is that these low-cost sensors are becoming more and more ubiquitous in our society. More and more people are using them, which is not bad. But the thing is that we as researchers have a certain responsibility to provide adequate tools to assess and approve accuracy. Because if we provide a certain amount of confidence that these results are good and that people can follow them, that means that they can take certain steps to reduce their exposure. So we're putting all these tools in their hands and allowing them to make these decisions themselves. So apart from policy issues to reduce exposure, this could be one of the major steps in the future to reduce health impacts from air pollution on individuals. I'd like to thank you for your attention and this opportunity to present my work. If you have any questions and comments, you can also find me on email, LinkedIn, ResearchGate, and I'd like to thank my institute, the Icarus project, and the Slovenian Research Agency. Thank you.
Okay, thanks, Rock, for the nice presentation. And so now we have time for a few questions. Alberto, do you have any?
Maybe I have one. Yes,
yes, please.
About the PM sensor. Is a portable sensor that is a very small device, I suppose, since you use it even during running. I wonder if it is able to really distinguish pollution from, for example, fog or high level of humidity.
It also has a humidity sensor in it, so we were able to make some corrections. But yes, these low-cost sensors, this is an issue that most of them have. This is I think it's quite a famous sensor. It's called a plant tower sensor that is in this device. It has some corrections, but yes, the humidity issue still has to be addressed with this kind of sensors. That's completely true.
Yes, but not only humidity, fog. I mean, a small particle of water.
Yes, I agree. Yes, so water particles are still an issue here.
Okay, that is okay. Thank you.
Thanks. So any other questions? So if not, I have a curiosity concerning the say classification accuracy. So if I correctly understood, so when you mentioned the accuracy was the overall accuracy, right? And not specifically, so kind of activities with more exposure to PM and less exposure on the other side. So, and you mentioned that somehow you may have some problems because you cannot distinguish easily between different activities that maybe they're not really so dangerous because you have no such a great exposure to PM. But so going deeply and looking at the activities, more dangerous. So is the accuracy still the same, or you can have a way to distinguish better, and so maybe the accuracy is getting higher?
Well, the thing is that the higher the concentrations of PM, so the higher the exposure, the more accuracy we would presume to get. But as the classification showed, and I used the R and VK environments for this, it showed that in this case, at least, the PM concentration didn't really play a lot of, didn't have a lot of weight in the end when classifying the activities. But again, My speculation is that this is again related to the difference in hour and minute data recorded. So this is one of the main things I have to fix in the next few weeks, and I hope that then we can actually see this difference.
Yes, it's always critical to discuss about the the quality of the data set. And so, as you mentioned, the granularity of different measures so can have an impact. Yes, actually. Yeah, I totally agree. Yeah, good point. Good point. So is there any question? Any other questions? I don't see any. And so, Rock, thank you again for the very interesting presentation. Thanks, everyone. So let's meet again after this short break, I will say for a coffee in 5 minutes to start exactly at 11 o'clock. Okay, thanks, everyone. Okay, welcome back. I think it's now time to restart. And next presentation is going to be delivered by Madhumita Pandiaraja. I forget, sorry for my pronunciation. And she is from the University of Cambridge. So please, floor is yours.
Thank you very much. I'll just share my presentation now. Okay, good morning to everyone. My name is Madhumita Pandiaraja. I'm a fourth-year medical student at the University of Cambridge. And today I'm going to be talking about the work that me and my colleagues have been working on about screening for atrial fibrillation, where we evaluated the efficiency of manual review of electrocardiograms from handheld ECG sensors. So just to give you a bit of background, atrial fibrillation, which is commonly referred to as AF, affects approximately 3.3% of the UK population. And it increases the risk of stroke by 5 times. So it's important to make a timely diagnosis of this condition. However, what we see is that about 3 in 10 cases of AF go undiagnosed because AF can occur intermittently and it can also be asymptomatic. Patients who are then diagnosed with AF are put on anticoagulants, which can help to reduce their stroke risk. And the prescribing of the anticoagulation is based on the assessment of their stroke risk using the CHADS-VASc score. So this is basically the criteria that is used in the CHADS-VASc score, which takes into account a number of factors, including the patient's age, sex, and specific comorbidities. So what we're hoping to achieve is that if we are able to roll out a simple and cost-effective screening program, then we can increase the diagnosis of atrial fibrillation and as a result, also improve our stroke prevention. So one of such approaches is using a ECG sensor, such as the one shown in on the screen. And this is a handheld sensor that individuals can use to make an ECG recording by placing their thumbs on it. So in our study, individuals were asked to make 4 recordings per day for a period of 1 to 4 weeks using this device. And then what it produces is a single lead 30-second ECG recording, such as this. So using an automated algorithm to analyze the ECG traces has been proposed as a strategy in order to reduce the manual review process more efficient. So the configuration of the algorithm determines the safety and potential benefit of adopting this approach. So with a more sensitive algorithm, we would be able to maximize the number of AF diagnoses that the screening test is able to correctly identify. At the same time, we want to maximize the positive predictive value of our screening algorithm so as to minimize the number of unnecessarily reviewed ECGs. So the aim of our work was to devise and evaluate the impact of 4 different AF algorithms and look at the effect of these 4 configurations on the manual review workload, as well as how accurately we are able to identify AF patients. So the retrospective analysis was conducted on the data that was collected through the SAFER feasibility study. And this data set consisted of 162,515 ECG recordings, which was collected from 2,141 adults who were aged above 65. And the participants of the study, as mentioned earlier, were instructed to take 4 ECG recordings per day using the handheld device for 1 to 4 weeks. So now briefly moving on to the methods that we adopted. So the review process of the ECGs firstly involved applying the Cardiolund ECG parser algorithm to the ECG traces that we collected. The algorithm then classified the ECGs based on signal quality as well as possible pathology. Following this, a first filter, who was a nurse in the context of our study, manually reviewed any ECGs that had been classified as pathological or low quality in order to rectify any misclassifications by the algorithm. The first filter also identified ECGs that needed further manual review to arrive at the diagnosis of an arrhythmia. So the third stage involved 2 expert reviewers who were cardiologists in our study, independently reviewing the ECGs that were identified by the first filter. And then any discrepancies in the diagnosis made by the 2 cardiologists were then resolved, and each participant was assigned a final diagnosis. So in our study, a total of 54 participants received a definitive diagnosis of atrial fibrillation. So using this data set, we assessed 4 different algorithm configurations. The first configuration consisted of reviewing all the pathological or low quality ECG recordings. The second configuration would exclude the low quality ECG recordings from manual review, but still include all the ECGs that were marked as pathological by the algorithm. The third configuration would involve being a bit more selective with the pathological ECGs. So only ECGs classified as having a fast regular rhythm or an irregular sequence would be manually reviewed. The fourth configuration would involve only reviewing ECGs that were marked as having an irregular sequence. So we then estimated the manual review workload that was associated with each of these algorithm configurations. And this was the total number of ECG reviews, both by the first filter as well as the 2 expert reviewers. So moving on to our findings, we estimated that the first algorithm configuration would require 20,155 reviews by the first filter and 2 sets of 5,005 reviews by each of the expert reviewers. And if we adopted configuration 2 instead, we saw that the total number of reviews could be reduced by 18.6%. However, what we noticed was that the reduction in the number of first filter reviews was much more considerable compared to the reduction in the number of expert reviews. And this is likely due to the fact that most of the low quality ECG recordings were being manually excluded by the first filter anyway in configuration 1. And with configurations 3 and 4, we saw further decreases in the total number of reviews, and the reduction was quite substantial. And with configuration 3, we saw that the total number of reviews would be reduced by 38.4%, while with configuration 4, we would see a 40% decrease compared to configuration 1. So a stricter algorithm configuration obviously comes with the risk of missing an AF diagnosis. So based on the configurations that we evaluated, we found that neither configuration 2 nor 3 would lead to any diagnosis being missed. However, with configuration 4, we saw that there was 1 patient who would have been missed out if this configuration was adopted. So based on this, it seems that the most favorable was configuration 3 in terms of both enhancing the efficiency of the manual review process while also maintaining the sensitivity of the screening test. So our analysis also highlighted the importance of having a 2-pronged approach to manual review, where we have a first filter followed by expert reviews. And we found that in all 4 of the screening algorithms, the first filter excluded the majority of ECG recordings prior to expert review. And this is beneficial for 2 reasons. Firstly, every review conducted by the first filter would then lead to saving us on 2 further reviews that would have then hypothetically need to be conducted by the expert reviewers. And another consideration is that it may be more cost effective, as it is likely that the expert reviewer's time might incur a greater cost compared to the first filter. Our work has a few limitations that are important to recognize. And the first of these are that we have assumed that all of the ECG recordings that were sent for expert review will be looked at. Whereas in reality, the reviewers will probably stop reviewing the ECGs once they find that an individual has one abnormal ECG recording, in which case they will not carry on reviewing the remaining ECG recordings from the same person. So we are likely to be overestimating the number of expert reviews needed. Secondly, ECGs that were classified as normal recordings by the algorithm were not manually reviewed, so we could have possibly missed out any false negative tests. And finally, the manual review workload was considered overall, and we did not take into account any differences in the cost of first filter reviews versus expert reviews, which would be pertinent in a cost effectiveness analysis. So future work, it would be very valuable for future studies to develop the ECG parsing algorithm further in order to boost the positive predictive value of the algorithm's pathological classification. And this could involve incorporating more details from the ECG signal trace, such as P-wave characteristics, rather than only analyzing the heart rate and regularity of QRS complexes, which is what it currently does. And we have previously reported a P-wave quality index at this conference as well, which might be useful towards achieving this. The ECG data collected from this study also provides an ideal opportunity to create a training data set, which can be used as a benchmark for to conduct reviewer training in the future. It would also be hugely important that future studies are able to prospectively verify the findings of our study. So just to conclude, we have independently verified the manual workload associated with the use of a handheld ECG sensor for AF screening, and our findings have reiterated the importance of an automated algorithm in identifying potentially pathological ECGs. And it has also highlighted the benefit of using a 2-pronged review approach, where we have a first filter followed by expert review. Furthermore, our findings also show that it is indeed possible to adopt alternative screening algorithm configurations that are able to significantly reduce the manual review workload without compromising the sensitivity of the screening test. And these are the references that were used. And before I finish, I'd like to thank the entire SAFER research team who have been involved in the feasibility study, which enabled us to carry out this study on the data set from the feasibility study. Thank you so much for this opportunity and for your attention.
Okay, thank you, Madam Ida, for the very interesting, nice presentation. We have a few minutes for the discussion. Is there any questions? Alberto?
Maybe one, yes.
Yeah, please.
At the very beginning of your presentation, when you started the description of your algorithm, you have mentioned a cardio-lung algorithm. Can you provide some details about this algorithm?
So I believe this is not an algorithm that we ourselves developed. It has been developed by a third party, and we have used it in our study to sort of verify how accurately it is able to identify AF. So I think the main elements of it is that it is analyzing the ECG trace based on both regularity of complexes as well as heart rate. And so this is where we think perhaps improving the algorithm to incorporate more details from the trace could be helpful in making it more accurate.
Okay, thank you.
Yeah, same line. I have a curiosity. So basically, if I correctly understood, so you first have a kind of automatic filter. So you have a data analysis done automatically. And I think this is not time consuming, right? It's quite fast. Yeah. And the main problem is the next step. So the part done by I would say by the doctors, so to check possible issues or possible something possibly done wrong by the automatic filter. Is that right?
Mm-hmm. Yeah, so the filter is essentially just helping us narrow down, but with ECG traces, there are a lot of artifacts, a lot of electrical noise. So it is hard for an automatic algorithm to be able to, you know, be accurate with identification. And even with the manual review by the doctors, that we did get discrepancies between two doctors saying there is something wrong versus someone else saying there isn't something wrong. So when there is even discrepancies in human interpretation, it might be more difficult to achieve that sort of accuracy with an automated process.
Okay, thanks again for the very nice, interesting presentation. Thanks, Madhumita. And I think it's now time to move to the next presentation, who's going to be delivered by Rimi Senthilnathan from TCS Research, India. Rimi, please, stage is yours.
Yeah, thank you for the introduction. Let me share my screen. I'm Harini. I'm doing my academic internship at TCS Research under Mr. Parijit Deshpande, who is a senior scientist at TCS Research. So my topic is about breath sounds as a biomarker for screening infectious lung diseases. So before moving on to the presentation, I would like to tell you that there is a QR code which I had put. If you want to see my textual abstract or paper, anything like that, you can just scan and go into the website and see in the Sci Forum website, and you can see. So there should be a motivation behind every project. So the motivation behind our project is as follows. Regular monitoring of breath sounds is essential for screening chronic diseases like asthma, COPD, the chronic obstructive pulmonary disease, and also the inflammation caused due to viruses like, say, the COVID-19 virus. Also, this screening needs to be done remotely and quickly. These tests are usually done in using a stethoscope in a hospital or a clinic, but in this pandemic situation, it is difficult for people to do so, to go to a hospital or clinic. So this needs to be done remotely. And affordability. So we have to do this with the help of the most commonly available in every household is nowadays the smartphone. So we have proposed to give a smartphone based solution that monitors breath sounds from the user via the inbuilt microphone, and our AI based anomaly detection engine analyzes it and gives them output. So this is a sample picture of myself who's holding a smartphone. So before moving on to the solution, I would like to give some domain. Breath sounds, as we know, is the exchange of air between the lungs and the atmosphere, which create a breath sound. Breath sounds can be broadly classified into normal and adventitious breath sounds. Adventitious sounds are the abnormal sounds that occur over the lungs and the airways. The term adventitious, what I mean is that audible lung sounds along with the normal sounds. So the crackles, wheeze, ronchi, and stridor each have their own particular abnormal sound in the lungs. The proposed solution is as follows, which has mainly 3 tasks. The first task is to pre-process the sounds acquired from the user. Second is to the breath sound detector, because some other sound other than the breath sound, so that or not. Next comes the anomaly detection engine, which is the main part. It detects if any anomaly is detected in the user's breath or not. So before moving on to the solution, I would like to give some points on signal processing features. First comes the MEL scale. MEL scale is the scale of pitches judged by listeners to be equal in distance from one another. So why do we need to go for MEL scale when we have frequency scale? The perception of human perceived frequency is not linear. So for example, imagine a 100 hertz sound playing in your head and you're listening to a 200 hertz sound. So if we compare the two sound, they have some perpetual distance. Perpetual, I mean, because we are measuring it using our gray matter, not a physical distance. So if we repeat the experiment by listening it for 1000 hertz and 1100 hertz, and similarly like that, the opinion of our perpetual distance might diminish. So in a given interval, the pitch of higher frequency range seems to be larger than the same interval at lower frequency. So this was solved using the Mel scale. The Mel scale was defined so that intervals that sound same also have same measurement in Mel. This is the formula which I had used for converting from frequency to Mel scale. So coming to Fourier transform, we all know that sound is a complex signal composed of multiple single frequency sound waves. So it is a mathematical concept that decomposes constant frequencies. So coming to spectrum, spectrum is a frequency content present in a sound signal, which is usually a pictorial representation called the spectrogram, which is the time versus frequency graph. And power spectral density is the strength of variations of power as a function of frequency. It shows at which frequencies are strong and which are weak. So if we could just hear harmonial piano sound, so we could see the overtones in the sound we heard. So similarly, we could see the overtones in the spectrogram and the power spectral density as well. So yes, coming to the Kepstrom. Kepstrom is Fourier transform of logarithm of spectrum. Since we apply a transform on the frequency spectrum itself, the resulting spectrum is neither in frequency domain nor in time domain. It is called Q frequency domain. So coming to the main feature which we had used, Mel frequency Kepstrom coefficients. It is a representation of power spectrum of a sound. It is they are the coefficient that collectively make up an MFC. So basically the audio signal is broken down into overlapping frames and FFT is applied. And here the filter bank means converting to Mel scale, and then the logarithm of Fourier transform, we get the Kepstrom coefficients. So here in these two graphs, the red ellipse shows the difference between the spectrogram of normal versus abnormal sound. So which we had used as a feature, this is, since it's a significant difference. And yeah, power spectral density, we could see that for normal sound, it is a little less than that for abnormal sound. So that is also used as a feature in this. So coming to the data sources we had used, for the breath detector, we had used the ECSA-7 data set, which has about 50 classes of environmental sounds. One of them is the breath sounds. So for the anomaly detection engine, we have used the Rail database, which is purchased by our company. And the Rail database consisted of these adventures, bees, crackles, ronchi, etc. Since this data set was unbalanced, SMOT algorithm was used. SMOT algorithm is nothing but synthetic minority oversampling technique, which is used commonly in case we have an unbalanced data set. So for each minority instance, k number of nearest neighbors are found which belong to the same class, and the difference between the feature vector of the considered instance and the feature vector of the nearest neighbors, which are k nearest neighbors, are found, and the difference vectors are multiplied by random number between 0 and 1, exclusively 0 and 1. So we get k different random vectors. So now the different vectors, after being multiplied by random number, are added to the feature vector. In this way, we get the synthetic object set. So this is what SMOT is about. Yes, coming to the solution we had used. So input audio signal is first normalized and bandpass. We have used bandpass filtering in order to remove the extra noises or contact turbulence, something like that. And so, next comes the feature extraction for breath detector, that is the MFCC. Depending on the frame size, the number of MFCC coefficients may differ, but in order to reduce the complexity, we had taken the mean of the coefficients corresponding to each frame. So after that, if it is a breath sound, then it will go for the feature extraction in the anomaly detection stage. If not, it will we are going to prompt the user to record again. So the main part in this is the anomaly detection engine, in which we had used two approaches. One is the machine learning based approach. In this, we had used MFCCs and power spectral densities, and they are used as input to different machine learning algorithms like logistic regression, KNN, like that. And coming to the deep learning approaches, in this we had used spectrogram images of the audio samples as feature. Considering the effectiveness of deep learning in classifying images, we had used convolution neural network, the usual one which we use for classification, and the I had also used ensemble CNN, which is slight variation of CNN, and the CNN GRU model, which is a gated CRNN model for classification. So this is the gated CRNN model. The spectrogram, this is sample of the model. The spectrogram image is led through the convolutional layers, and after that it is fed to bidirectional GRU, because LSTM is has more number of parameters than the GRU. So I went for GRU instead of others. So yeah, coming to the results, using the 3 different machine learning algorithms, I had used the voting classifier for 3 different algorithms, and average accuracy of 98% is achieved. And for the anomaly detection engine, 5 different machine learning algorithms was used in the first approach, and an average of 94% accuracy is obtained, like from logistic regression, SVM, artificial neural networks, random forest, and KNN. And in the second approach with CNN, ensemble CNN, and gated CRNN, we had about good accuracy for about 95%. But since we had, if we had more number of data, then accuracy might still improve for the deep learning approach. So this is just a user interface created, and this is the front end, and the back end AI engine is being hosted on AWS. It is running on the EC2 instance, and it is connected to this front end. Yeah, so future work involves the fine tuning of model by getting feedback from the users. Of course, on getting more data, we need to do the exact screening of the disease, like whichever disease is it, and also we can improve the accuracy on augmenting more data. So thank you for your patience listening, and thank you for giving me an opportunity to present this in a conference. Thank you.
Thanks, Sarini, for the nice presentation. We are now open for the discussion. I guess in this case, Stefan might have questions related to the algorithms.
Yeah.
Stefan, do you? Alberto,
Yeah.
I see you on.
Maybe.
Do you have?
Yes, I have a question.
Yeah, please.
Do you use data from a data set, an online data set, but I didn't get if you also record some data using the phone or not?
Yeah, exactly.
And in this case, if the frequency response of the microphone of the cellular phone can have an impact on your study or not?
Yeah, exactly. So we have the user had to measure the sound at a particular distance, so that we will not get the contact turbulence, and also we will get the required frequency. So we had set till now on basis of some experiments, we had set distance of about 20 to 22 centimeter from the mouth, like towards the microphone. So yeah, so that we will get the required frequency.
Okay, but changing the phone model, you can have a different acquisition, because each cellular phone has a different microphone, and there's and then it can have an impact on the acquisition.
Exactly. Okay. Yeah, exactly. So now this is done for Android phones. I think most of them having similar. This is done for a similar kind of microphone, but still we are expanding and collecting data for different iPhones and other Android phones, and we are populating our data set so that it would match any smartphone.
Okay, thank you.
Thank you.
Okay, thanks. I had a curiosity related to the impact of GRU, but sorry, but we are out of time. And we have to move to the next presentation. So thanks again, Rini, for the interesting presentation. And the next speaker is Aida Vidal-Balea from the Universidad da Coruña, Spain. Aida, please, the stage is yours.
Thank you. I'll share my presentation now. This article presents the development of a new collaborative application for Microsoft HoloLens to smart glasses. During the last years, augmented reality has been incorporated in the educational field. For example, it has been applied for helping with different subjects and skills like language spelling, high school chemistry, or to learn to play piano, for example. Augmented reality can bring many benefits to the mentioned applications, including immersiveness, collaboration promotion, remote guidance, and gesture recognition. In addition, this type of technologies help teachers to foster students' interest in learning certain subjects and abstract concepts in novel visual ways. The main objective of this paper is to use the potential that augmented reality has to create the possibility to have augmented reality-enabled lectures and practical lessons. Specifically, it proposes an architecture for providing low-latency augmented reality education services in a classroom or a laboratory. The proposed communication architecture consists of 3 layers: the augmented reality and IoT device layer, the edge computing layer, and the cloud layer. As it can be seen on the figure, at the bottom is the augmented reality and IoT device layer. In this layer would be the users that wear the Microsoft HoloLens 2 glasses, as well as the IoT devices. Both augmented reality and IoT devices are connected either through a Wi-Fi access point or a gateway to the edge computing layer, where the AR educational services are executed. In the middle, we can see the edge computing layer, which is conformed by 2 sublayers. The AR service sublayer that makes use of edge computing devices to provide fast distributed responses, and the AR IoT service sublayer that allows for interconnecting AR and IoT devices seamlessly. When the edge computing layer is not able to respond to the request from an augmented reality or IoT device, it can ask the top layer for help. This cloud allows remote users to view and to manage the stored data and the provided services. The implemented application was successfully tested in a real classroom, but in order to test it in a realistic use case with multiple students and AR devices simultaneously, an in-house developed 3D ray launching simulator was used. This helps us to obtain estimates of the quality of service in the proposed scenario, ensuring accurate results in order to analyze the feasibility of the proposed AR system, which leads to a good user experience. In this image, you can see the 3D model of the classroom with which the simulation was made, which is based on a real classroom, where the Wi-Fi access point is on the ceiling, in the middle of the class. In this image shows the scenario created by the 3D ray launching tool and the simulation results that illustrate the estimated received signal power for both 2.4 and 5 gigahertz operating frequency bands of the HoloLens 2. For this development, the Microsoft HoloLens 2 smart glasses were used, which can be seen on the image. These smart glasses provide stereoscopic vision and integrate the images and objects on the real world. Microsoft provides a toolkit that facilitates development aspects as gaze or gesture recognition. The implemented application provides features for educational video watching and remote guidance. The teacher is able to control remotely when and how the AR content is displayed on the smart glasses used by the students. Here you can see 2 screenshots of the app, which was created using a universal Windows. This part of the application was created with Unity and Microsoft Mixed Reality Toolkit that were used to implement the 3D model visualization part of the application. As it is illustrated on the image, this provides guidance through step-by-step multimedia content that includes the visualization of animations and 3D models, which can be moved, rotated, and scaled by the user. This feature is really useful during labs and required to make use of certain tools or to assemble or disassemble hardware components. This paper presented an AR teaching system based on Microsoft HoloLens 2. The AR system architecture based on edge computing devices was designed to provide low latency services and to ease the interaction between IoT and AR devices. In order to tackle potential quality of service limitations when the AR system is deployed with a high number of students, preliminary Wi-Fi radio channel measurements and simulations have been obtained through an in-house developed 3D launching simulator. Thank you very much for your attention.
Thank you, Aida, for the very interesting presentation. We have now quite a lot of time for the questions. So anyone in the audience? Okay, I start. So you said that, so basically you started by doing a kind of, say, analysis or preliminary, say, analysis of the applicability of this tool. But have you started already to run it into any school?
Currently, it's still a demo, and because of the COVID situation, we couldn't test it in a real scenario with more students. And that's why we did the simulation process to test the
simulation only. And curiosity, is it expensive, a system like this? Because you know that, so in Europe, I mean, in Italy, and I think in Spain it will be quite similar. So we have big problems related to funding. And so for the schools to provide this kind of systems to the students, it will be quite expensive, I guess, or not. So in economical terms, any idea, any suggestions?
Well, we use the HoloLens glasses because we had access. We had access to them, but I think any other device could be used with this architecture, and the idea would be more or less the same.
But for the schools in, yeah, so I was meaning in terms of budget, is it an expensive means, or would it be kind of economical one instead?
Sorry, could you repeat the question, please?
So in practical terms, is it expensive or not, a system like this for an entire school? I mean, not for just a single classroom, but for an entire school.
Mm-hmm. I think the more expensive would be buying the classes for each student.
Sorry, we didn't catch. So to buy the glasses,
yeah, smart glasses.
But I think you cannot. You can assume that school is teaching like this, and you have to tell the students to buy their own glasses. So you have to provide, right?
Yeah.
Okay, thanks. Alberto?
It's okay for me. Okay.
Okay. Is there anyone else? Okay, so if not, let's thank Aida once again for the interesting presentation. Thanks, Aida. And let's move to the next presentation. Valentina, we are a bit early, so you can take a bit more time if you like for your presentation. So next speaker is Valentina Bello from the Università di Pavia. Valentina, please, stage is yours.
Okay, I'm sharing my screen. Okay, so thank you, Professor Mariani, for your introduction. It's a pleasure to have the opportunity to present my work that is titled A Near-Infrared Spectroscopy-Based Approach for Detection of Fluids in Rectangular Glass Microcapillaries. I carried out this activity with the help of my colleague Elisabetta Bodo. We are both PhD students at the Laboratory of Electro-Optics of the University of Pavia under the supervision of Professor Sabina Merlo. So here it is, the outline of my presentation. So first, I will tell a few words about what microfluidics is. Then I will introduce the goal of our work, and I will describe the micro-optofluidic configuration that we set up in our lab for the experimental measurements. And I will also give you a better insight in the theoretical model that we developed. I will go on with the results, and after the conclusion, I will tell a few words about what's coming next, so about the future perspectives. So, microfluidics is a really interesting disciplines that have been gaining a lot of importance starting from the 90s. Basically, it is the science of manipulating and testing fluids, usually in the range of microliters down to nanoliters in network of channels with typical dimensions that ranges from tens to hundreds of micrometers. So basically, when we do microfluidics, we put a fluid into a microfluidic chip. Then we run some measurements that are based on usually optical or electrical or electrochemical readout method. And then we extract some information about the properties of the fluids. Microfluidics is applied in a wide range of fields such as biology, healthcare, chemistry, drug discovery, and many others. So the goal of our work is to exploit rectangular glass microcapillaries to do micro-optofluidic sensing. So basically we are combining microfluidic with an optical readout technique. We are using these devices because they have several appealing features. First of all, they are low-cost devices, so they cost a few dollars each. Then they strongly reduce the issues related to light scattering because of their rectangular cross-section. Then they are transparent, so they are suitable for optical detection, and they have micrometric dimensions, so they can be exploited for the analysis of ultra-low volumes of sample. In previous work, we have exploited these devices to measure the real part of the refractive index of fluids using either spectral reflectometry or spectral shift interferometry. But there is a but: refractive index sensing is non-specific. This means that if we have a combination of fluids, several combination of percentages of these fluids can induce the same variation of refractive index. So basically, we don't know the exact composition of our sample. For this reason, in this work, we want to exploit microcapillaries for the detection of fluids based on their spectroscopy properties in the near-infrared region. So in this case, we want to exploit the properties of the imaginary part of the refractive index. In this picture, we can see the rectangular glass microcapillaries, and here the typical dimensions of the device that we exploit for this work. So here you can see the schema of the microfluidic setup that we used to carry out the experimental measurement. So all the analyses were remote, non-contact, and non-invasive. The capillary is laid horizontally onto a bulk aluminum mirror. Light from a tungsten lamp is shined onto the flat surface of the capillary. It crosses the channel once, it bounces on the underneath mirror, and then it crosses the capillary once again. The light, the output light, is collected by a lens, and it goes toward an optical spectrum analyzer for the reconstruction of the wavelength spectra of the output light. The fluid goes inside the channel simply by injection with a syringe. Before proceeding with the experimental measurement, we developed a theoretical model to have a better insight in the principle of operation of our device. So we have taken into account the effect of absorption of the samples by applying the Beer-Lambert law. And then we computed the path traveled by the light in the channel and in the capillary by computing the Snell's formulas. We also calculated the percentage of light that is transmitted at each interface by applying the Fresnel formulas. In the end, we computed this spectral response that is defined as duration between the spectral power obtained with the channel filled with the sample and the spectral power obtained with an empty capillary that is filled just with air. So, coming to the results, in this plot, we can see that there are some solid lines that are the experimental spectral responses, and some dotted lines that are the theoretical predictions. We tested water and 3 different types of alcohol: ethanol, isopropanol, and ethylene glycol. First of all, we can see that there is a very good agreement between the experimental measurements and the theoretical prediction. And in particular, we can say that it is possible to distinguish all the samples, and in particular to distinguish water from the alcohols, because water has this very strong peak absorption around 1.450 micrometers. Then we did a little further step. So we developed a configuration where the light path traveled in the channel has been extended. And with this configuration, we repeated the measurement, inserting in the channel ethylene glycol. Here I reported the power spectra for ethylene glycol obtained in the 2, let's say, configuration. The blue line refers to the result that we obtained in the traditional scheme, while the orange line is the power spectrum obtained with this extension of the light path in the channel. So we can see that when we extend the length of the interaction between the light and the sample, we can reconstruct the absorption profile of the sample with a higher level of detail, because in this case, we can distinguish much better these 3 dips that correspond to the absorption peak of the ethylene glycol in this spectral region. So in conclusion, in this work, we have reported a microoptofluidic platform based on rectangular glass microcapillaries for identification of fluids based on their spectroscopy features in the near infrared region. I showed you our experimental setup with the microcapillary that is laid on a bulk mirror. And also I explained the theoretical model that we implemented in MATLAB environment to investigate the performances of our device. The experimental measurements are in good agreement with the theoretical prediction, and it is possible to distinguish water and several types of alcohols. Moreover, by extending the light path inside the channel, we can obtain better results because we reconstruct the absorption profile of fluids with a higher level of detail. About the future perspectives, there is plenty of work to do, because we would like to realize a more compact setup, including laser diode and the photodiode instead of the tungsten lamp and instead of the optical spectrum analyzer that is really bulky. And also we want to substitute the bulky mirror with a metallization coating that is realized directly onto the external surface of the glass wall of the capillary. Moreover, both sides of the capillary can be coated to obtain a multiple bounce configuration that extend a lot the interaction between the light and the sample inside the channel. With this configuration, indeed, we can obtain measurement with higher sensitivity. And for example, we can also investigate fluids in which, for example, an alcohol has been diluted with small percentages of water, because in this case, we can strongly enhance the contribution of water around 1.450 micrometers, as I showed you before. Then I want to underline one last time that our setup and our measurements are completely remote, non-contact, and so non-invasive and totally safe for the sample. For this reason, this system could be exploited also for the analysis of biological fluids. So from my side, it's all. Thank you so much for listening, and also thanks to our supervisor, Professor Sabina Merlo.
Thank you, Valentina, for the nice presentation. We have time for a few questions. Anyone? Alberto, please.
Okay. Do you think that it's also possible to launch the light along the main axis of the capillary in order to increase the interaction?
Okay, yes, but the problem is that doing in this way, there is a bit of, let's say, I think it's not really handleable, because you have to handle the microfluidic path and also the optical system in the same direction. One of the advantage of our system is the decoupling of the microfluidic path and of the light path, because you have your fluid that is flowing inside the channel, and all the optical components are above. So the two paths are completely decoupled, and this is really one of the advantage of the system.
Okay, yes, you're right. Thank you.
You're welcome.
Okay, so I have a curiosity. So you showed in slide 6, so in the theoretical curves, there were some cases, some kind of waviness. And in the experimental data, instead, you didn't catch this waviness. So what is it really related to in that specific case?
Oh, you mean in this slide?
Yeah, so the blue line, so you see for a wavelength of around 1.4 micrometers. So you have in the theoretical plot, the blue at the top, the blue related to the isopropanol. Yeah, so you have this waviness, and it's so you have some others even for less than 1.2 micrometers. So what's the physical reason for this waviness that you don't catch with the experimental data?
So you mean let's say the difference between experimental result and theoretical, right?
Yes, though they're very, very close, so they're good. But,
So for example, in this region, because our lenses are working better in this region, so around 1.4 micrometers. So indeed, if you observe all the spectra, you see that there is a little mismatch in general for wavelengths that are lower than 1.2. So the reason for this mismatch, I think it's related to the lens, because the performance are a little bit are not so good for wavelengths lower than 1.2. And about this waviness, it could be that the losses that are due to the passage between different media are higher than, let's say, the contribution due to absorption. So that could be the reason why there is this mismatch. I think that could be a reasonable explanation.
Okay, thanks. Other questions? I have another curiosity related to biological fluids. So in that case, is the system working the same, or I mean, if you have a kind of transport inside the system of micro or nanoparticles, so in this case, specifically nanoparticles, so can you still detect everything? So do you have any interaction or a change in the kind of response you measure?
Okay. The main problem that I see in that case, I think it's about scattering, because if you have a lot of particles in your flow, maybe there is a lot of scattering. So it could be that the signal that is coming out is very low. So maybe you should have some problem about, let's say, signal to noise ratio. So in this moment, that is the main problem that I see with the fluids containing a lot of particles.
Okay, thank you so much. And let's thank Valentina again for her very nice presentation. And let's move to the next speaker, who is Matteo Torzoni from Politecnico di Milano. Matteo, please, stage is yours.
Hi, thank you, Stefano, for the introduction. Can you hear me? Yes?
Yes.
Okay, I'm now share my screen. Okay, good morning, everybody. My name is Matteo Torzoni, and I will present you the work entitled Combined Model Order Reduction and Deep Learning Approach for Structural Health Monitoring under Varying Operational and Environmental Conditions. Before to start, I would like to thank co-authors Luca Rosafalco and Andrea Manzoni. Okay. In their lifetime, civil constructions are called to face several challenges, including material deterioration and unexpected loadings. Together with the poor maintenance, these sources of degradation might compromise the structural performances. As an example, the shocking collapse of the Morandi Bridge has been a key event in the recent engineering history in creating a new awareness about the importance of structural monitoring. A promptly detection of structural damage and deterioration can greatly reduce the maintenance cost over time and prevent catastrophic events. To this aim, structural health monitoring looks for strategies to keep track of the structural health and to detect, locate, and quantify the damage occurrence. Thanks to the advancements of sensor technology, health monitoring strategies are always more often based on continuous vibrational measurements. In this setting, the monitoring process involves the observation in time of a structure to extract some damage-sensitive features useful to determine the health conditions. Moreover, health monitoring strategies are always subjected to some environmental variability, which is able to potentially hamper the monitoring task. Particularly, daily and seasonal thermal fluctuations can affect several material properties and induce a geometric distortion. Here, we propose a data-based approach for damage localization under varying operational and environmental conditions. I'm going to use this simple example of a clamped beam to give you the main points of the methodology. In order to accomplish the localization task, our idea has been to take advantage of the great modeling capacities of deep learning. But as you probably know, in order to perform the learning process, we need data. Unfortunately, dealing with civil constructions, data involving damage conditions are often unavailable. So the idea is to replace real measurements with numerical experiments in which we simulate the effect of damage. We model structural damages as local stiffness reductions of predefined subdomains assumed fixed within the observation interval. Moreover, we take full advantage of our simulations by also modeling the thermomechanical effects of contraction, expansion, and stiffening, softening by imposing some temperature profiles on the structural model boundaries. From our simulations, we collect vibrational signals shaped as multivariate time series and temperature measurements, both mimicking the recordings of a pervasive sensor system. These data are collected for several operational and environmental conditions for each damage scenario we consider. The classifier is then trained on this data in solving the inverse problem of identifying which is the damage condition behind the processed data. If we give a closer look at the methodology, we can split it down into two stages. During a preliminary offline phase, after having evaluated the operational and environmental conditions, we build a structural model parameterized with respect to thermal and loading actions. This is denoted as full order model. Then, to relieve the computational burden associated with the dataset construction, a parametric model order reduction technique is adopted to replace the full order model with a cheaper reduced order model. And then, exploiting this reduced order model, a dataset is constructed by collecting several vibrational and temperature recordings alongside with the associated labels. Once the dataset is ready, we can train the classifier in mapping this data into categorical labels. During the next online phase, the trained classifier is used to process new signals to categorize the current structural state, providing information about the presence and the localization of damage. Our classifier relies on a peculiar deep neural network architecture called fully convolutional. Through the convolutional layers, we can extract damage-sensitive features useful to determine the conditions. These features are extracted from the vibrational recordings. Then, these features are merged with the temperature recordings in order to provide some support to the classifier in recognize the thermal effects within the observed dynamics. As I said, during the training phase, the classifier learns the underlying mapping between the input instances and the associated labels. In order to do that, the learning algorithm tunes the parameters weight by minimizing a loss function over the dataset. Coming to the modeling aspects, we use the thermoelasticity linear theory with a one-way approach to simulate the two-field coupling, and we neglect the temporal dependence of the thermal field. Moreover, we disregard damping effects and we introduce a local dependency of the stiffness matrix on the material temperature. Finally, we model structural damage as a selective stiffness reduction of predefined subdomains with variable magnitude within the interval between 5 and 25%. As I said, the dataset construction is accelerated by using a reduced order model. Here, our reduced order model relies on the reduced basis method, and we use the proper orthogonal decomposition technique in order to construct the projection basis. Thanks to this reduction step, we can highly alleviate the numerical complexity of the problem while keeping under control the level of introduced approximation. And coming to our case study, the methodology is applied to the monitoring of a two-dimensional frame. The structure is subjected to low-intensity seismic loads, whose accelerogram are numerically generated by means of empirical equations as functions of local magnitude, epicentral distance, and site geology. Moreover, the structure has been subjected to the imposition of temperature profiles imposed on the structural model boundaries and generated for the temperature data of the city of Milan. In addition to the damage-free baseline, we considered 8 damage scenarios, each one involving a selective stiffness reduction of a subdomain with variable magnitude within the range between 5 and 25%. The sensing system is composed by 11 sensors, recording both structural accelerations and temperatures at the same location. Here, I want to highlight how adopting the reduced order model, the computing time required by each simulation over a time interval of 35 seconds reduces from 421 seconds to only 5 seconds with a speed up of about 86 times. Here are reported the classification results. The first 2 graphs are the learning curves regarding the evolution of the loss function and of the global accuracy during the training, while the testing results are summarized by the confusion matrix, which shows how the testing instances are classified with respect to the target labels. Here, in absence of any experimental data, our testing instances were provided by the full order model. We obtained a good global accuracy of 81.5% with 2 main sources of error standing out. First, we note how testing instances labeled as 6 and 3 are misclassified as respectively 3 and 1. This is because of their similar influence on the mechanical behavior. Secondly, we note how the majority of misclassifications is about confusing damage with undamaged configurations. This is because of the presence of a variable damage level, which of course implies an augmented difficulty in distinguishing between the 2 conditions. And coming to the conclusion, we have proposed a database strategy for structural health monitoring under varying operational and environmental conditions, integrating model order reduction and deep learning. The damage localization task has been performed by making use of vibrational and temperature measurements. To overcome the lack of experimental data, a database of synthetic recordings has been built offline for a set of predefined damage conditions, and the reduced order model has been exploited to accelerate the dataset construction. Finally, a deep learning-based classifier has been adopted to perform the automatic feature extraction and to relate raw sensor measurements to the structural health conditions. Concerning the proposed case study, we achieved a global accuracy of about 81.5%, which is a very good result in the light of the heterogeneity of the explored conditions and of the damage level variability. Concluding, we can say that the jointly use of deep learning, model order reduction, and sensor technology is very promising and could lead to very important innovations in the structural health monitoring field. Okay, I finished it, and thank you all for your attention.
Thanks, grazie Matteo for the nice presentation. We are now open for discussion.
If I well understood, your dataset was populated using simulations. So now I know that the focus of your work is the deep learning algorithm, but do you think that can be of relevance to take also the uncertainty of your measurements into account?
Yeah, for sure.
Maybe in the future.
Yeah, absolutely. as in this case, for example, we didn't corrupt the signals with white noise or similar, but we already tried with some sort of corruption, for example, and the procedure can work. Yeah, we have to investigate, for example, the uncertainty, for example, a source of uncertainty can be the material parameters, and this of course can be investigated and must be investigated, which is the impact of this kind of uncertainty on the procedure, for sure. Yeah.
Okay, thank you.
Okay, thanks. So Stefan probably cannot unmute himself, so but he wrote a question on the chat, so he's willing to know something related to the architecture of the neural network and some information concerning the time for the training.
Okay, as I said, the architecture is built upon convolutional layers. It's called the fully convolutional architecture, and this kind of networks are usually used for image recognition, but here are adapted to the analysis of 1D time series. And important aspects are the number of filters each convolutional layer feature. Here we adopted the scheme 16-32-16. And the other question with regard to the times of training, most of times in reality is needed by the population of the dataset, while the training time is relatively small. In this case, was about 40 minutes, while the population of the dataset was more than 3 hours. In this case, we used 15,000 of instances for the training. So it's a lot of data. And if the convolutional architecture is devoted to the analysis of the time series, we don't need the same procedure for the processment of temperature data. In fact, the temperature data, being just punctual data and not time series, they don't need to be processed by the convolutional layers, but are just merged through a concatenation block to the features extracted from the vibrational recordings.
Okay, thanks.
I don't know if I have an answer to the question. If you need more details, I can give.
Guess so.
Okay.
Yes, I assume so. Yes, so the main problem is, as I said, that probably Stefan cannot unmute himself, and so that's why he's not able to reply. So sorry, Matteo. Okay, Matteo, thanks again for the very interesting presentation, and it's time to move to our last speaker. Our last speaker is Tiago Cabral from the University of Campinas, again in Brazil. So Tiago, welcome, and stage is yours.
Thank you. Can you hear me fine?
Yes.
Oh, great. I'll share my screen just a sec. I'm here to present my research, which is about health monitoring of bonded joints between pipelines during the assembly and operation of these joints using embedded fiber vibrating sensors. This study was conducted at the Laboratory of Metrology and Automation of the Federal University of Santa Catarina under the project CHIC2, the Chirography for Inspection of Composites, which was financed by Petrobras. Here's just a quick outline of the presentation, and starting with the motivation of this study. Our previous presenter talked about structural health monitoring and its importance with civil infrastructure, for example. In this case, in our study, we are focusing on fiber reinforced plastic pipelines, which are increasingly more common, especially in oil platforms or gas lines in the gas and oil industry. And the importance here is that joint failure can disrupt operation, which causes significant financial losses. And also when you're dealing with oil, you can have severe environmental contamination if this leaks for some reason. And here we have a picture of several pipes with These are glass fiber pipes, and each one of these are bonded joints. They are bonded or cemented balanced pig adhesive joints, which you have two pipes here, which are joined by an adhesive layer between them. And this creates the demand for monitoring and inspection of these joints to ensure structural integrity and also to increase operational security and minimize downtime of operation. There are some standards worldwide of how you can inspect these joints with hydrostatic testing, ultrasound testing, radiography, or other techniques, but they are only applicable to certain stages of the pipeline life cycle. They can be difficult to execute on the field because of the harsh conditions or confined spaces, and they are not capable of long-term monitoring. So we believe that the integrated instrumentation approach can offer some promising prospects, such as reduced costs. They do not disrupt the operation when you're measuring with them. You can monitor hard to reach locations because you integrate them into the pipeline and then they can just be there wherever they are needed. They are protected from ambient conditions since they are embedded into the structure, and they are capable of long-term monitoring once installed. So the proposal of this work then is to use integrated instrumentation for axial strain monitoring using fiber optic sensors embedded into the adhesive layer of these bonded joints, like we have in this schematic drawing here. Have the pipe here, two sections of pipe. Here is the bonded joint with fibers enters inside this layer where the fiber sensors are positioned. Then you can interrogate the sensors and see how the structure of the pipe is done. On to the design of the test specimen for the experiments we conducted. We have a 3D representation of the test specimen here. It has two straight pipe sections joined by a sleeve, and in one end it's closed by an end cap, and the other you have a flange so you can pressurize the pipeline. And if you look at the section that's inside the sleeve, it's like this. It's like a spigot with this design. You have a section with slightly lower wall thickness here, so you can fill this with the adhesive. And this length that will be inside the sleeve is double insertion depth. For this case, it's 57 millimeters. This will be important for the instrumentation design. And for the sensors, we are using fiber ratings, which are very simple, and there's ample technical literature available for them. They are highly applicable in structural health monitoring. They are fairly simple to use. They are basically a periodic modulation of the refractive index of the fiber core, as it's showing this picture here. Here's the fiber, and you have this periodic modulation, and this works as a spectral mirror, a narrowband spectral mirror. So you have an input signal which is broadband here in the wavelength domain, and you have a reflection that's very narrowband, and most of it's transmitted. We are going to interrogate it in the reflection. So the peak wavelength of the reflection is given by the Bragg condition. So lambda Bragg is equal to 2 times the effective refractive index of the fiber core for the fundamental mode, and the period of the refractive index modulation. When this fiber Bragg rating is subjected to temperature and mechanical loads, they change the effective refractive index and also the period of the grating. So this sensor is capable of monitoring both strain, mechanical strain, and temperature changes. Since we're not interested in temperature for now, our tests are conducted under laboratory conditions with controlled temperature. So we don't have the crosstalk here in our measurements. And for the instrumentation design, we have a drawing of the fiber here, the sensing fiber. We're using 3 fiber Bragg ratings per fiber, which give us 3 strain sensing points per fiber. And then we are using about 12 fibers per test specimen, so it's 36 points of strain measurement per bonded joint. And we can get a strain map of the whole joint like this. Each fiber ratings has a different nominal wavelength, so we don't confuse the sensors. And there's plenty of spectral separation between them to avoid overlap due to non-uniform loading. We're also using a Teflon tube here to protect the fiber when the part of the fiber that's outside of the adhesive, and the standard FC connector for interrogation. The preparation of the test specimen. Here's a pipe section that will be inserted into the sleeve. There's a slide machining here, so we have space for the adhesive in the fibers, just like in the joints used on the field. And you can see here side by side, this is the test specimen, this is the fiber, so you can see the sensor's orientation right here. So FPG1 is closer to the inner edge of the sleeve here. It will be deeper in the bonded joint, while FPG3 is closest to the exit point of the sleeve. And FPG2 is between the both of them. So I have 3 string monitored points here and 36 total around the joint. First, for the insertion process, we bond the fiber chips to the wall of the pipe. This avoids breakage of the fiber when we are preparing the sample. They can bend and break if you don't secure them. And to further secure them in place, we then place the adhesive first in the just in the fiber position. This is a 2-component adhesive especially for this kind of pipe. Then we can distribute the adhesive over the whole pipe and also in the sleeve. And we bring them both together very carefully, and we can check if all the sensors survived and what strain levels they are currently measuring. And it's also worth noticing that one of the test specimens we prepared has 3 planned defects, which we are going to see if we can detect. A small circular defect, a small square defect, and a larger rectangular one. They are made with Teflon sheets because they don't bond very well to the adhesive, so it creates an adhesive failure. And in one side, we're using aluminum tape so they can be easily noticeable in computed tomography scans. So this is what I was referring before. We prepared 3 test specimens that I was referred to as S1, S2, and S3. So the first one, S1, was prepared with severe lack of adhesive. We used very little adhesive here to create lots of defects. S2 was prepared to be as sound as possible, the best of the 3. It will be our reference joint. And S3 is the one with the intentional defects. All of them are subjected to a computed tomography test for our reference purposes, and we use 12 fibers per test sample here. So here are the computed tomography reconstructions of the 3 joints, S1, S2, and S3. The darker spots are voids, where we lack adhesive. So you can see in S1 there's a lot of dark spots, which is a severe lack of adhesive here, as we expected. In the second one, we have some little dark spots all around the place, which is a bit of porosity, which also expected with this kind of technique. And for the third one, we have a little bit less porosity, but we can see clearly the circular defect here, the larger rectangular one in this place, and the smaller square is around here. The first test we are going to execute with the sensors themselves are the adhesive curing strain, which is conducted right after the curing process, which is this picture right here. For this test, what we expect is that the strain map should be entirely negative or compressive strain as the adhesive shrinks as it cures. And we are using maps, 3D maps here. This is a surface plot and this is a color plot, which is just a top view of the surface map. We have 36 points here of strain, and then we just interpolate this linearly in both axes here, the FPG axis and the optical fiber axis. And the first and the last optical fiber here are repeated values, so you can have the 360 degrees of the joint. And here we have FBGs 0, 1, and 2 that corresponds to 1, 2, and 3 on the previous drawings. So this is the data for S1. As we can observe here, it's very evident that strain levels fluctuate intensively. And we have positive strain here, so tensile strain, and both compressive strain, which is not what we expect for a healthy joint, a sound joint. And this tells us there are probably a lot of defects here, as we are very far from the ideal, which would be the results from S2 here, which is significantly different from S1, as you can notice. First, we have all negative strain, as we expect for this experiment. And this, on the optical fiber axis here, we have pretty good symmetry, circumferential symmetry, which is expected for a tubular structure. Here we don't have symmetry at all. And we can see there's very clear difference between a sound joint like this one and the joint with a lot of defects here. But it's interesting to see what happens when you have planned defects, such as in the third test specimen here. In this case, we only see a negative strain too, but it's not as uniform as the second one. We can notice some features here. It's not possible to outright say the position of the defects from this test alone, but as it deviates significantly from the ideal, we can flag this for further inspection down in the production process. And then we prepared this test specimen for hydrostatic testing. But before that, we can conduct one more test. If you notice in this picture here, when it's all prepared for this hydrostatic testing, it is supported from below in 3 points here at the end cap and 2 points around the sleeve itself. That's right here. And this 2 point support around the sleeve creates a flexural loading, which is 0 on the supports, and then increases linearly until the middle portion of the sleeve, where it's the maximum value, and then decreases again to 0 on the other support. So there's a slight flexural loading here, and we can use this to our advantage. For example, if we rotate this test sample around its axis, it's like shifting this load from, say, this bending axis to a bending axis on another plane. So it's just like, virtually, it's like introducing a new load into the sleeve here. And this is important.
Sorry,
because, yep.
Sorry, please come to the conclusion because it's already 12:30.
Okay, so we can create this load here, and you can see that what you get is very like we expect from this kind of loading. And just moving to the final one here, which is more interesting, the hydrostatic testing. We expect it to be entirely positive, and we can see with this one, with the planned defects here, we can clearly see the circular defect and some artifacts on the larger defect here, which are significantly different from the good one, which is very smooth strain map. So to conclude, we have a sensing setup to detect and monitor defects in bonded joints between pipelines by measuring axial strain. It's adequate to monitor the assembly of joints of the pipelines and during operation. And some further studies are required for the practical field measurements, such as compensating for temperature. That's it for me. Thank you.
Okay, thanks, Tiago, for the very interesting presentation. So I think we have time for one quick question, if any.
Quick question about the number of FBGs.
Yeah,
you
sure.
choose three FBGs. Do you think that is useful to increase the number, or maybe it's possible to reduce the number? Why do you choose exactly 3 FBGs?
Sure, let's take a look at this image again with the insertion depth here. We have 2 points here of stress concentration because of geometry changes. That is the far side of the sleeve and the outside of the sleeve where the pipe leaves the the section here. So these are the most important points where you have stress concentration, obviously, and it's important to measure these two. So minimum amount of FBGs, 2 FBGs to measure these points. And it's interesting to have at least one more to see what's in between.
Okay, thank you.
Okay, thanks. So I think it's now time to end this student session. I think that our big applause goes to all the speakers today. We would like to thank them all for the very nice and interesting presentation with this very diverse environment. So really thank you for the very interesting and pleasant session we had. So let me just finish by saying that the next session will be Monday morning. And at the end of this session, we are going to announce the winner of this competition for the best student presentation. So I let the stage to Anna for the concluding remarks at this point. Thanks to everyone.
Yeah, I just wanted to also thank you, everyone, also to you, Stefano, for chairing this session. And I also wanted to remind everyone for the next session on Monday. So it's everything. Thank you on behalf of MDPI, and I hope you enjoyed the event.
Thanks everyone. Bye.
Bye-bye.
Thank you. Goodbye.
Thank you. Bye-bye.